All right, welcome back. I hope the test went well. Section 3.1 and 3.2 are basically application sections. So we're just going to go through a bunch of different examples, and they're representative of almost every problem you'll get that looks like these, and they're basically all have the same, there's like 6 or 7 different archetypes, and they all fall into one of these types. So the first is growth and decay models. Think populations, right? These are like the most simple population models. Think like radioactive decay. Right, radioactive decay. These are the simplest growth and decay models, right? Population growth, population decay, radioactive decay. Yeah. Normally they're written as dx dt equals k times x, right? And k here is the special number. This is the constant of proportionality. If k is positive, you have growth. If k is negative, you have decay, right? So this says the change in x over time is proportional to the amount of x you have, right? The change in x over time is equal to k, some number k times the amount, right? So how fast you're changing depends on the amount and this constant of proportionality. And you initialize it, right? At t0, you have some initial amount of stuff. These models are nice and separable, linear, so you can solve them using either integrating factor or separability, right? Take your pick. Normally, the questions revolve around finding k, right? Given some initial condition. So they'll say like, at time 0, you have this amount of x, and then at time 1, you have this amount of x, right? And they want to know what is k, right? What's your constant of proportionality given this change in time? Here's an example. We got bacteria in a petri dish. We have initially some P0 number of bacteria, right? It doesn't really matter how much it is. And after 1 hour has passed, the number of bacteria is 3/2 the original amount, P0, right? So we went from P0 to 1.5 P0. If the rate of growth is proportional to the number of bacteria, Pt, the time t, this sentence right here, right? This tells us that we have growth and decay model, right? The rate of growth, dp dt, is proportional to p, right? dp dt proportional to p. That means dp dt is some constant times p, right? That's what it means to be proportional to. That's the giveaway that we're in a growth and decay model. Our goal is to now determine the time necessary for the number of bacteria to triple. So if it takes 1 hour to go from p to 1.5 p, how long does it take to get to 3 p naught is the question, right? The question is, how long does it take to get to 3 p naught? Here's the info we got. P at 0 is p to 0. P at 1 is 3/2 p naught. And dp dt is kp. The growth rate is proportional to the number of bacteria. What we want to know what t gives p of t equals 3 p naught. Step 1, solve for p, right? Find an equation p of t, right? Find an equation p of t. dp dt equals kp implies you can solve this via your favorite thing, but we'll do it via integrating factor since that's nice and repeatable. Move the pk across the equal sign. We get integrating factor set up here, right? This is my thing I'm going to integrate in my integrating factor. Mu t equals e to the integral of negative k dt, which is e to the negative kt. And then cut to this step. Really, we're multiplying on this side by e to the negative kt, but it's times 0, so it doesn't matter, right? integrate both sides. That cancels off the derivative. We get a plus c over here. Divide both sides by e to the negative kt. Divide by e to the negative kt. Dividing by e to the negative kt is like multiplying by e to the kt. Now, we have an expression for p in general. And we want to use the two conditions that we have to find k and c, right? So we have two conditions if we look back up here, right? We're given p1 and p0. We know p0 and p1. These are my conditions, right? Since I have two equations here and two unknowns, I can solve for c and k, right? So p of 0 equals p naught is the easy one. Plugging in p of 0 into this expression gives c, right? p0 equals c times e to the 0, which is just c. So c equals p naught. So that means my expression for p of t has been updated to p naught e to the kt. And then I use my second condition. P of 1 is 3/2 p naught, which means when I plug in t equals 1, right, I get 3/2 p naught equals p naught e to the k, which means, dividing by p naught everywhere, e to the k equals 3/2, which means, taking natural logs of both sides, right, that k equals the natural log of 3/2, which is approximately this number. So this is k. This is k. I now have everything, right? P of t equals p naught e to the stuff times t. And the question is, when does this equal 3p naught? Right? What is t? When does t give this equals 3p naught? So we solve. We set 3p naught equal to this function, and we're looking for t, right? Looking for t, divide both sides by p naught, take the natural log of both sides, divide by 4.4055, t equals natural log 3 divided by 0.4055, which is about 2.71 hours. Okay, here's another one, radioactive decay. We've got a reactor converting stable uranium-238 into plutonium-239. After 15 years, it is determined that 0.043% of the initial amount A naught of plutonium has disintegrated. Find the half-life of P239. If the rate of disintegration is proportional to the amount remaining. Again, this tells me I have dA dt equals Ka, right? Since A is the amount. A is the amount. Side note, half-lives are simply the time it takes for 1/2 of the atoms to, in the initial amount, to disintegrate, right? So a half-life means after some time, right? A of t equals 1/2 A naught. That's 1 half-life. And they told us after 15 years, this amount had disintegrated, right? I think these are also backwards. It should convert plutonium into uranium, but it's okay. So anyway, they told us after 15 years, it's determined that 0.043% of the initial amount has disintegrated. And remember that A of t is the amount of plutonium at time t. So we know at time 0 we had some initial amount, right? Some initial amount of plutonium. And at 15 years, this percent had gone away, right? They said that 0.0043% was gone, which means we're left with this amount of A naught. And we know the disintegration rate is proportional to the amount remaining. So we get a nice linear decay model. We want to know what is T whenever A equals 1/2 the original amount. We know from the previous example that all the solutions will look like this, right? Because once you solve one of these equations, you've solved them all, because you just replaced the letter A, right? You just replaced the letter A with a different letter. So you know that A of T is going to be C times e to the kt every time. Well, we know that A of 0 is A naught, which means C is A naught. And we know that A of 15 is this amount A, which means this amount A naught equals A naught times e to the 15k. Again, cancel the A naughts, take the natural log of both sides. The e's cancel, divide by 15. And we get k equals 1/15th natural log of this, which should be a negative number because it's decay, right? Should be a negative number. So this is now our expression, right? Oh, where'd it go? Yep. We plug this in for k, right? Plug in this number for k. That's our expression for A of T. And the question was, what's the half-life? So we just set 1/2 A naught equal to the equation for A of T. Which means just solving for T, right? Take the natural log of both sides. The e's cancel, divide by this number. We get T is about 24,000 years. Right, 24,000 years. Here's some carbon dating. Some more radioactive decay. The ratio of carbon-14 to the stable carbon-12 in the atmosphere and all living things is a constant ratio. When a living organism dies, the absorption of C14 stops. Breathing, eating, photosynthesis, etc. So, by comparing the proportion of C14 in a dead thing to that of the atmosphere, we can determine its age as long as we know the half-life of carbon-14. This is exactly how carbon dating works, right? And the number that you should use in the homework if it asks you is 5,730 years. So the commonly accepted half-life of carbon-14 is this amount. Okay, here's another growth and decay model for you. Except this time, it's not exactly proportional to the temperature, it's proportional to the difference in the temperature and the ambient temperature. Right, so let's talk about Newton's law of cooling. So we're going to let T be the temperature of an object at time t, and Tm be the constant ambient temperature of the medium around the object. Think like room temperature, right? Like the room temperature is a constant, and it's ambient, and it can take as much energy as it wants, and it won't change, really. Right? So, the change in temperature per unit time is proportional to the difference in the temperature of the object and the temperature of the room. So what this means is, if the temperature of the object and the ambient temperature are extremely far apart, you're going to grow or decay faster than if the temperatures were closer together. Let's look at an example. When a cake is removed from an oven, its temperature is 300 degrees Fahrenheit. This is my T, right? 3 minutes later, the temperature is 200. This is now T of 3, right? So I went from T0 of 300 to T of 3, 200. And the question is, how long will it take for the cake to cool to the room temp of 70? Right, T of what equals 70? And they told us the room temperature, right? This is the ambient temperature of the air. This is the time 0 temperature, and this is the time at 3 minutes temperature. And so we know that dt dt is k times t minus 70. This is separable, right? This is separable. This is the t part, move it over. This is the little t part, move it over. I've got 1 over t minus 70 equals dt equals k times d little t. I'm going to integrate both sides, right? This will cancel out these things. This is natural log absolute value of t minus 70. And this is the integral of kt dt is just k times t plus c. Right? Taking e to both sides, right? The e and the natural log cancel. I get e to the kt plus c becomes c kt. We've seen this a few times, right? Because you can split this into e to the kt, e to the c, which just is a constant times e to the kt. Handwriting got bad at the end there, sorry. And then adding 70 to both sides, right? Plus 70 on both sides, plus 70. Over here gives you t equals 70 plus c e to the kt. And since I know t of 0 and t of 3, I can solve for c, and I can solve for k. So my temperature is 70 plus 230 e to the negative 0.19018 t. And I put in notes here. I don't really like this question because temperature won't ever be 70 in any finite amount of time, since this number is never 0, right? This is never equal to 0, which means you always have 70 plus a little bit, right? 70 plus a little bit, always, since this is never 0. But however, after a while, 30 minutes or so, right, the temperature gets down to 70.77 degrees, which is pretty close. Pretty close. So these are all growth and decay models, right? The things we just did are all growth and decay models. Okay. Next up, mixtures. Let's let A of t be the amount of some substance, usually it's salt. Normally it's salt. And let's say we are pumping in a brine solution, right? A brine solution means a salt solution. Brine is salt, right? Brine is salt water. So we're going to let A of t be some amount of salt, and then let's say we're pumping in salt water into a big tank, and at the same time it's draining out the bottom. Then the rate at which the amount of salt in the mixing tank is changing is given by dA dt equals input minus output, right? The change in the amount of salt in the tank per unit time is the input rate of salt minus the output rate of salt. Usually we abbreviate this to Rn minus R out. Rn minus R out. Now here's an example. Say we have a 300-gallon tank containing a salt solution, right? A 300-gallon tank containing a salt solution. And we're going to pump in a brine containing 2 pounds of salt per gallon at 3 gallons per minute. The well mixed solution inside the tank is pumped out at the same rate, 3 gallons per minute. If there was initially 50 pounds of salt dissolved in the 300-gallon tank, find the equation AT for the amount at time t. What happens as t goes to infinity? So here's the picture I always draw for these tank problems, right? I start with this big tank. I know this is not a really nice looking tank, but it has some salt water in it, right? Salt water. We're pumping in salt water. 2 pounds per gallon is the concentration at 3 gallons per minute. Inside the tank, 300 gallons of water, or salt water, excuse me, and at time 0, there's 50 pounds of salt, right? 50 pounds of salt. And we know that the mixture is exiting at 3 gallons per minute, right? The first thing we should note is that since the input rate of actual salt water and the output rate of salt water are equal, right? These are equal. That means that the amount of salt water in the tank will always be 300 gallons, right? Since we're pumping in as fast as we're draining, that means there's always 300 gallons in this tank, right? This number. Always 300 gallons in the tank. This is when, what do they call it in physics? Dimensional analysis, right? Comes into play. This is the equation setup that we know we have, right? The change in salt per unit time is the rate at which you pump it in minus the rate at which you pump it out. And we're given that the initial amount of salt, A of 0, is 50. 50 pounds? Yeah, 50 pounds of salt. Just pay attention to the units, right? Pay attention to the units. What are the units of dAdt, right? This is pounds. This is minutes. So this is measured in pounds per minute, right? Since it's pounds of salt, minutes of time, dAdt is in pounds per minute, right? It's a rate. It's a rate. Pounds of salt per minute. Also, I recognize that this is a very American problem because we're using pounds and gallons and minutes instead of kilograms and liters and seconds, right? Or I guess we could still use minutes. Those are pretty universal. But pounds and gallons are very American units. So it doesn't really matter. All that matters is you match up things. So since this is in pounds per minute, I need this and this to both be in pounds per minute. These both need to be in pounds per minute. Well, if I know that they're pumping in 3 gallons per minute and it's 2 pounds per gallon, the question is, how can I multiply or divide these two numbers to get pounds per minute, right? It's pretty easy to see, right? Pounds per minute is equal to pounds per gallon times gallons per minute, right? Pounds per minute is pounds per gallon times gallons per minute. So in order to get my rate in, I just multiply 3 gallons per minute times 2 pounds per gallon. The gallon units cancel, and I'm left with pounds per minute. Same with the rate out, right? Same with the rate out. So I multiply 3 gallons per minute, that's the output flow, right? And then I need the concentration, right? I need the concentration of salt water leaving. Well, the concentration of salt water leaving is the amount of salt in the tank. Amount of salt, in tank. Oh, poop. Amount of salt in tank divided by the gallons of salt water, right? Is the amount of, I guess just the amount of water, right? So it's the amount of salt, which is A, pounds at any time, divided by 300 gallons. That's the concentration. And if I multiply that by 3 gallons per minute, I should get pounds per minute. So the out rate is 1 over 100 A pounds per minute, which means my my equation that I need to solve is dA dt equals 6 minus 1 over 100a, given that a of 0 is 50. And this is linear. This is linear. So all I need to do is move this across the equal sign to get this equation. And now this becomes my p of t function, right? And I'm going to integrate. Mu of t should be e to the integral of 1 over 100 dt, which gives me mu equals e to the 1 over 100t. All right, so I multiply mu on both sides. I integrate both sides, right? Integrate this side dt. When I integrate this dt, I get 6 times 100 e to the 1 over 100t. And on this side, I just cancel out the derivative, right? So I get 600. Oh, and I add a plus c. Don't forget the plus c. And then by dividing both sides by e to the 1 over 100t, right? I cancel here, I cancel there, and then I divide here by e to the 1 over 100t, and I get c times e to the negative 1 over 100t. This is now my amount of salt at every time. This is my equation for the amount of salt at every time. And since a of a naught is 50, I know that c equals negative 550. Which means this is my true equation, right? And the question was, what happens after a long time? Right? What happens after a long time? Well, as t goes off to infinity, this term here is going to head to 0. Which means this whole term is going to head to 0, which means I'm left with a at infinity, right? As t goes off to infinity, a tends to this 600 pounds. And wouldn't you know it, if you check the concentration of that, 600 pounds of salt and 300 gallons of water is 2 pounds per gallon, which is the exact same as the input concentration, right? So what happens is we start with some salt water, right? We're pumping in a solution that's 2 pounds per gallon, and after a long time, the whole tank will be 2 pounds per gallon. Which totally makes sense, right? That totally makes sense. So these are the tank problems. Next up, series circuits. Electrical engineering time. You can either have a LR circuit, which has a resistor R and an inductor L. And in this case, the setup looks like this. You've got some EMF, right? Electromotive force. You've got some inductor, L, which is given or drawn with curly things. And then you've got some resistor, R. All right, so this is the basic setup for an LR series circuit. And Kirchhoff's second law, so you're going to be talking about the current, right? I is going to be the current. I think it's the current in the wire, they say. The other thing is the charge across the capacitor that comes in later. But this is Kirchhoff's second law, says the inductance times the rate of change of current per unit time plus the resistance times the current should be the electromotive force at time t, right? Or the impressed voltage at time t, right? So a lot of times you think about this as being like a battery or something that's like sometimes giving power, sometimes not giving power. So it may be like a strange EMF here, but like this is something that can change with time, right? Okay, this is Kirchhoff's second law. Right? In the case of a capacitor circuit, you're going to talk about something across the capacitor, I guess. You talk about the charge across the capacitor is really what you talk about. So in this case, Kirchhoff's second law says that the resistance times the charge on the capacitor the change in the charge over the capacitor per unit time plus 1 over the capacitance times the charge is equal to the impressed voltage. And the important relationship here is that Q, the charge across the capacitor, is the integral of the current per unit time. Right, it's the antiderivative, which means that I is the derivative of charge with respect to time. So here's a question from the homework. A 200 volt electromotive force is applied to an RC series circuit that has resistance of 1,000 ohms and a capacitance of 5 times 10 to the negative 6 farad. Find the charge if there is, at time 0, there is 0.2 current in the system. Find the charge at t equals 0.004 seconds, and find the current at the same time. So we want a general expression for QT, and we want to know the exact value of QT and current at these times. Okay, here we go. And the last but not least is find the charge as time goes to infinity. Okay, so since we're in a resistor capacitor series circuit, right? We have a RC series circuit. We're going to use Kirchhoff's second law, which says that the resistance times dq dt plus 1 over cq is equal to the electromotive force, or the EMF. And they told us in the problem that the resistance is 1,000 ohms. 1 over c, the capacitance, this was the capacitance, 5 times 10 to the negative 6th, which means 1 over that number is 200,000. And they told us the electromotive force, the battery, right, is 200 volts. Which means 1,000 dq dt plus 200,000 q equals 200, and this is a setup for a linear differential equation, right? But in order to find the integrating factor, we need to divide by 1,000 everywhere, right? So divide by 1,000, divide this by 1,000, divide this by 1,000, and we get dq dt equals 200q plus 200q equals 0.2. And again, you find the integrating factor, right? You integrate this, e to the integral of 200 dt, to find the integrating factor. You jump from here to here. You integrate both sides, right? Integrate both sides. Integration over here kills this off. Integration over here gives you 0.2 divided by 200, e to the 200t plus c, which means, solving for q, divide by e to the 200t, divide by e to the 200t, divide by e to the 200t. Qt equals 0.001 plus c e to the negative 200t. They also gave us I at time 0, which was 0.2. And we know that I is the derivative of q with respect to t, which means I equals dq dt, which equals negative 200 c e to the negative 200t. And since we know I of 0 equals 0.2, that means 0.2 equals negative 200 c, because this term will go to 0, which means c equals negative 0.001. So we now have our expression for q in general. That's part 1, find qt, right? Now we need to know what is q of 0.004 and what is I of 0.004, right? Q at 0.004 is this number, right? Just plug in that for t, coulombs. And to get I, you just plug it in, you just take the derivative of q and then plug in that t, right? So this goes away, you bring the 200 down, this many amps. And the next question was, what happens after a long time, right? As t goes to infinity, Q will tend towards 0.001 coulombs. Okay, that's it for 3.1.